I would like to direct your attention to this C++ program right here. Now, it seems like a simple program at first, but you might already start having some questions. For example, why am I using fill and setf instead of iomanip? Now, I can't explain that to you. I just like doing it this way. But what I can explain to you is what this is and what this is, and so on. Now, we'll start with the first thing. We first declare a CPPB bytes object. We call that buff. Now, I might have already guessed this is just a byte buffer object. Now, the implementations, you're probably not interested in it, so I will not go over it. It's just imagine it's a vector byte, okay? Now, we take the instruction of add, and then we take the RMIMM operand encoding for width 32, which is D word. We're encoding that instruction into the byte buffer. Now, if you're not familiar, this is the x86 64 instruction set. You should probably go read up on that before you continue watching, because it's going to be a bit confusing. But basically, this is the mod field of the mod RM byte. We are setting it to 01. Now, if you don't remember that off the top of your head, just the displacement 8 plus register address thing. The register in question is BP, which is pretty common. If you have a stack frame, that's for the local variables. Displacement of 4, which is not actually common. You usually use a negative displacement here, but just bear with me for a second. And we skipped the immediate for now, so we don't encode it. After we encode this instruction, we take the return value and we get the offset of first immediate. Now, you might already guessed this just gives you the offset of the immediate with respect to the instruction base. Now, why is this useful? Well, you might sometimes want to just write the immediate in later. It's also very useful for generating relocations, but we're not getting that today. But anyway, we will get that offset, we'll add it to the buffer's data pointer, and we get an address. We are writing 30 into that address with this function. Now, what is this? If you look at the hover hints, it's actually very obvious. The WV is just a convenience type def that I have. It takes in a width enum value, and it just spits out whatever unsigned int type corresponds to that width. And this write function, it just writes a little endian version of that number with that width into this byte buffer. Now, again, you should not concern yourself with the implementation here. It's really not very interesting to look at. But the story today actually begins in this instruction namespace, or more precisely the x86 namespace. So we'll jump to here now. So when we enter the x86 namespace, you might first notice some utilities like addb, which is just operator plus for the SAD bytes, which is not in the standard library. We're using this namespace, CPPP literals, but actually we only care about this literal that it defines, which is _b for an STD byte literal. You just need to know that exists now. We are bringing the CPPP bytes class, which we've talked about before, just the byte buffer, into the global or the x86 namespace. It will be used a little bit later. We define an enum class with which just contains the normal enumerators you might expect for all the different width options, 8 to 64 bits. We have a header function with the byte count that will convert a width enum into a number, which is how many bytes is corresponding to that width. We also have this enum, which is actually not important for now, so we'll just skip it. This WV, we already talked about that too. It's just a long chain of conditionality. Basically, it takes in a width enum value and it just spits out the type that corresponds to the value. WVS, same thing, but it's signed because some of the instructions actually sign extend your immediate operands or your displacements, so it's important to let the user actually pass in signed values. For the registers, it's just the normal conventional register values. It goes ACBP, SPBP, SIDI. You probably know that already. There's also H through DH, which actually require a prefix to access, but we will not concern ourselves with that for now. Also XMM. This is the REX prefix values. You probably already know that too. The interesting part begins in the detail namespace with the pack type def. Well, not type def, the struct. This struct has a variadic template and nothing inside. Normally, you don't see structs with nothing inside. Usually, you see structs with something inside. Even if only static members, that's still something inside, but this is just empty. Now, the reason that this is empty is actually because we are only concerned about using this type in partial template argument deduction, which we'll talk about immediately after now. But basically, you can have a pack like pack int, and char, and so on, and it will be a type that encapsulates all your types in a single array. We also define some simple operations on the packs, like pack concat, and you can already see the partial template deduction coming in handy now. So for pack concat, we like to accept two types, which hopefully are pack instantiations. But for arbitrary types t and u, there's nothing for us to do, so we just define nothing. Now for the case where t and u are both pack instantiations, we can use this syntax, which is partial template specialization, to actually extract the type stored in the t and u packs, even without actually accessing any member of those types. So this is the interesting construct we'll be using from now on, so you should be familiar with it. So the pack ts here will be inferred from the t type, and it will give us the packs that are in the the types that are in the t pack, and us are the types that are in the u pack. And we will then define a type def type, which is just the pack containing all of those elements together. We'll also define a convenience type alias pack concat t. You probably already have seen this many times. It's about the same thing in the stdlib type traits header. We just basically make it less annoying to type. Pack concat n here, the same idea basically, but now it concatenates an arbitrary amount of packs together. Now you can pause the video to read this. It's not really that complicated. It's not rocket science. Well, not rocket science compared to the stuff that's about to come next. Now this starting to get interesting. This pack apply to. So P is actually a pack here, and we have an operator which is actually a template, a type template with two type name arguments. And we also have a type name u, which is actually a type. It's not another pack, it's just a type. And what this is supposed to do is actually applies, like for each type x in the pack t, we'll have x op u as the result, and we'll return all the results in a new pack. So with pack apply to, you can see how it works. And the op as a type template will assume that it has a type member, and it will take that. And this is not that complicated either. We just use the normal pack expansion to basically map the OP-TS-U type expression over the entire pack of TS. And again, we have the type def for convenience. And now we have an outer product. Now if you know APL, this is just the dot operator from APL, outer product. So basically we take all the types X from pack T and the types Y from pack U, and we run the binary type operation OP on X and Y, and we return a pack of all of such results. Or you might think of it as taking each Y, or here US, in U, and then transforming each of that into a whole pack containing one operation result for each type in T. And after we do that, we concatenate all of the packs together, basically a Ravel operation, and we'll get our final outer product result. So that's how it's implemented. You can pause and ponder if you are not that familiar with this concept and you need to think more about how it works. And after that, we define an enum class component type, which is the different components that an instruction can have. Now, you might see that we are missing some things like the SIB byte, for example. We just removing those for simplicity because, you know, this is already quite complicated. Again, we have something just like pack, which is an empty struct. Now this time, the encoded component struct, it encapsulates a component type enum value and assigns the n, which is basically how many bytes that component actually ended up in the final encoded binary instruction. In the detail, we also define an offset of first struct, which basically it goes through an array or a pack of encoded components. It finds the first component with the matching type, and it sums up the width of all the components before it to find out the offset of the first component that is relative to the beginning of the instruction. You might already remember that we used it here. And finally, we define encode feedback struct, which is basically like a pack of encoded components, but with actually some members this time. Hooray! So we define total size, which is just fold with all the sizes, and also an offset of first, which uses the aforementioned helper template to help you find the offsets of the first instruction components with certain types. We also define a struct for concatenating encode feedback objects or encode feedback instantiations. It's about the same as pack concat, so nothing interesting here. Encode feedback symbol is just a helper type alias to create an encode feedback pack with only one component encoded in it. And now let's go on to all the possible instruction components. We have an opcode which contains a REX prefix and operand bytes. Now the REX prefix is optional. If it is 0, then we just ignore it, otherwise we'll encode it. The reason why the REX byte is part of the opcode struct is because it always comes immediately before the opcode bytes and after any optional prefixes or stuff like that. So we just put it here, and we create an encode member which takes a byte buffer and just writes the corresponding bytes. Also returns a value of this monstrosity type, but basically just a type that has this opcode component tag on it, and it also records the size of the instruction encoded using the n template argument. We also have a type def overload, which is a pack containing a single empty pack. So this is, reading by the name, is all the overloads that this component supports. And this component only supports encoding with no extra arguments. Now, you will always want to encode to byte buffer, so that's not included here. And we also have a helper type def opcode NR, which just saves you from having to type out 0 REX prefix value. Opcode plus R, so that is for those instructions where you basically have several consecutive, or actually 8 consecutive opcodes, which each correspond to a single register destination argument. So we just have that here. It's about the same thing. We'll not dwell on it for a long time. It's an optional prefix. It's literally as simple as can be, just a single byte. We just append the byte to the byte buffer, nothing else. And now we have the immediate. Now this skip immediate T is not an instruction component. This is just a tag type for skip immediate, which we've actually used before. But basically what this does is it let the immediate be uninitialized, and we'll figure it in later. And after that we'll have in a details namespace we'll have a generic struct called immediate of type, where T is the type of the immediate, and we define 2 overloads, one for the particular, like a concrete value of that type, and one for skip immediate T, where we just call this RESB, which is actually identically named to directive in the NASM assembler. Basically this reserves bytes to be initialized. And we define the type def for immediate, absolute immediate, and sign immediate. So for immediate, if the width is 64, then we use a signed 32-bit because it's sign extended. Otherwise, we just use an unsigned value of the normal size. Absolute immediate is always of the corresponding size, even for 64 bits. Now, 64-bit immediate is mostly used for the MOV-ABS instruction, which is actually just the MOV in the SDM. It's commonly called MOV-ABS in all the assemblers, because the only difference is that the immediate can be 64 bits. Sign immediate, just the same thing as immediate, but it's always signed regardless. A displacement is also not an instruction component, because yes, it is part of the instruction, and if you look at the SDM, it's actually an instruction component, but here the component specifically refers to something that always exists given an instruction encoding. And you might know that a displacement only exists if the mod.rm byte's particular value dictates that it exists. So even if you're using a certain instruction encoding, you don't always have displacement. Only if your mod rm byte refers to a memory address with a displacement do you actually have to put it in. So that's why it's not an instruction component here. It's actually just a helper type for function overloading. So you might remember that std has a similar type for distinguishing an alignment in the operator new. Now it's kind of obscure, but it's about the same idea. You just wrap a simple integer type, but it's a distinct type, so overloading doesn't get confused. We also have skip displacement, which is like skip immediate, but for the displacement. Now we actually need to record the width here because the mod rm byte's value is not known at compile time, so you have to provide extra information at compile time to tell it whether you have an 8 or a 32-bit displacement. Simple as that. We also have the mod rm byte here. Now for some instructions, the opcode /reg is used for part of the opcode. For other instructions, the field is used for a register operand. To deal with that, we just define two clearly invalid opcode /reg values and to use them to signify that it actually corresponds to a register argument as either the destination or the source. And in detail, we have a helper template, which is just for simplifying the return types. Basically, for each kind of mod rm, you either have just a mod rm with 1 bytes, and after that you will have a displacement with a certain amount of bytes, depending on the displacement width. This is a mod rm with displacement. We have a helper struct here because we need to instantiate it with all the different possible widths to generate all the overloads. So this is for displacement, skip displacement. It's for RDST, which means rm reg, the opcode /reg field as the DST, so we'll place it in front. And so RSRC, which is the same thing, but this is in the back. And here we have our mod rm struct. We inherit 3 times from mod rm with displacement to generate all the overloads for the different supported width types. We also define all our supported overloads, and then we define a additional version for no displacement. And similarly, we have explicit specializations for RDST and SRC, which use the helper templates as described above with the appropriate argument lists. These are useless. Ignore those. I'll delete them later. And further, we'll have encode config, which is a helper template for encoding your component signatures. But to understand this, we actually should look afterwards to this. So an instruction encoding class is basically the heart of our encoder. You can instantiate it with several template arguments, which are instantiations of the above-mentioned components. And it will take all the components, figure out all the possible combinations of overloads from all the components, and it will generate all the possible instruction overloads. So actually, if you look at the IDE hint here, you can see that it actually generates all the overloads for you, and you have 14 overloads. Now, in a traditional C++ library, this will just be a variac template, and you just see t ... or whatever, and then you will not actually know what possible types you can pass in. And also, you probably don't want to rely on implicit conversion in that case, because the library might handle it badly. But in this case, it's all generated explicit overloads, which makes it actually super editor friendly, and you also get the benefit of implicit conversions and the default intuitive if you write C++ for a long time, but still intuitive overload ordering rules. And this is the primary template, which concerns only the case where there are no types, because that's the only time where this will be instantiated. So we define one overload, which takes nothing, and we encode nothing. Very straightforward. An instruction with no components, you do nothing when you encode it. And now, if there is at least one component, then we use this encode comp class. We inherit from it to have all the actual overloaded encode functions. We also can look at the overloads type there first. We do an outer product between all of comp's overloads, which is this component overloads, and all of the possible overload combinations for all the rest components combined. we do the outer product with respect to the pack concat helper, which basically concatenates all the pairs of overloads together to form a longer argument list. And that will give us all the possible final overloads. And here we pass in the component, basically all the rest of the components combined into a single instruction encoding class, which, by the way, all the instantiations of the instruction encoding classes are also valid components in their own right because they define overloads and the encode member. So that's why we can just treat it as a big component containing everything else, and our outer product between these overloads. But here we actually need to distinguish between all the arguments in this component and all the arguments in the next component, because we want to forward the former to the current component's encode function and the latter to the rest of the component's encode functions. So that's why we use the detail t-pair helper instead, which actually creates a pack of a pair of types instead of just concatenating them and losing any information about which is which. And then we can look at encode comp, which inherits from encode comp sig for all of the combos, which is basically here this outer product. So basically, the outer product gives you all the pairs of this component and the rest overloads, and that will give us the combo pack. And we go through each of the combos here. By the way, you cannot overload resolve between functions inherited from different base classes, so we also need to use this using to basically explicitly inherit all the functions into this scope of this class, so they can actually be overload resolved with respect to each other. And that's a minor detail though. And in encode compsig, we'll basically have a pack of 2 packs, which contains this arguments and the other arguments. And we define encode function here, which does take a byte buffer, arguments for this, arguments for the other, and it dispatches to the corresponding encode functions. We also again report all of the component encoding details through the return type. Unfortunate that we have to spell this again, but deco type, and then concat. We'll get all of the component feedbacks collected into the return type. And don't forget return, by the way. If you don't write the return statements, actually UB, you do not get a default constructed return value, just UB, so don't do that. Just, return empty braces, be safe. So that's basically the heart of the encoder, but there's also a little bit more I want to go over. In the detail namespace, we have select by width, which takes IE8, IE16, IE32, and IE64, and width. Now, if you read it, it's pretty obvious that basically what it does is that depending on the width, it selects either IE8, IE16, IE32, or IE64. Now, the intention is for you to use this to define a for width like this. So we have an instruction encodings class, which basically you can instantiate with 4 instruction encodings for the different widths, and then it will define this for width member for you, which will let you select different encodings based on your operand width. If you look back at our test program, it comes in handy here. So RMIMM is a type def to instruction encodings, well actually regular instruction encodings, but that is also a type def to instruction encoding. And we can just directly say for width W32, and it will just select the correct corresponding instruction encoding type for us, which is extremely nice. Now we observe that many of the x86 instructions actually share similarities for the different width versions, so we define some helper templates to be more dry. So this is RIE. RIE stands for regular instruction encodings, by the way. We have variable width, which is actually another empty struct, and actually wraps a template which takes a template argument of a non-type width. Well, width is a type. It takes a non-type argument of type width. And what this does is basically this is intended for use with the aforementioned immediate family of components. And what you can do with that is you can say RIE variable width immediate. And basically it will encapsulate the idea that you want to encode an immediate here, but you have one tab its width vary depending on our current instruction width. We also have an opcode substitution here and a plus R opcode substitution for opcode plus R. Basically what they do is, because many instructions have different opcode for the 8-bit and the 16 to 64-bit versions, but everything else is the same. So we have an opcode substitution helper to help us substitute out the opcode for the 8-bit version while keeping all the other components intact by default. In the detailed namespace, we have an IE reify width helper, which basically, whenever you encounter a variable with a wrapper around some template, we actually instantiate the template with a concrete width as specified here. And also subs opcode, which actually helps perform the opcode substitutions as described here. And also insert REX prefix. This is extremely straightforward. If we find an opcode or a plus R, we just or the REX prefix we want into here. So for example, for the 64-bit version, we can automatically OR in an rex.w field in there. We also have do reify for 8-bit with for opcode substitution. You will substitute in the opcode and also do reify for width 8. But also, there are some instructions for which there are just no 8-bit versions, so we also support subs to be void, and we just define type as void so you will not use it. And finally, we have helpers to actually do the reification. For 8-bit, we do this. We explicitly support having void for subs. For 16, we just do it normally. We add a 66 prefix. For 32-bit, we do nothing. It's the default reify for 32. For 64-bit, reify for 64. Also add a with REX prefix. Simple enough. Regular instruction encodings basically performs all of the tasks for you. You just have to provide the components and the substitutions for the 8-bit version. Now, if this is void, then you don't get an 8-bit version. Otherwise, you will perform a substitution for the 8-bit version, and it just defines instruction encodings for all of the bitnesses using the algorithms as defined before. The regular short instruction encodings for instructions without 64-bit versions, like jumps. There are no jumps with 64-bit relative addresses. For relative long instruction encodings, we have instructions that do not support 8 or 16-bit versions. Like for example, move 0 extent from 16-bit. So we don't support 16-bit here. Now, for instructions that support 16-bit but not 8-bit, you just use regular instruction encodings with void as the first one, as I mentioned. That's also covered. Now, there are some very common instruction patterns that will encapsulate here. So in the instruction namespace and in a detailed subnamespace of that, we have the ins RMR struct, which will encapsulate this kind of instruction, where we have an RMR encoding where the 8-bit version has some opcode and the 16 to 64-bit version has that opcode plus 1, and obviously because it's RMR, we have a register operand as the source. And for this one, for ints, in addition to the RMR version, which is inherited here, we also define an RRM version, which is base plus 2 and base plus 3 respectively. So for example, if the RMR is 80, that would be 80, 81 for RMR, and 82, 83 for RRM. And we also have the corresponding Marr-Ales field here. It's very straightforward. We also have RMI version here, which is RM, IMM, also for 8-bit and 16 through 64. We also have a variable with immediate depending on the width of the instruction. That's mainly relevant for 16 and 32-bit because they use different width immediates. For add, sub, CMP, and move, they are actually perfectly encapsulated by the aforementioned patterns, so we just inherit from them. For move, there's also like other encodings. Like this is not comprehensive, by the way. It's not exhaustive. It does not contain every single possible instruction you can have. For example, this does not have the mov-q. It does not have segment selector move. It's just a simplified version, proof of concept. The RIMM is also provided here because mov ABS uses encoding, and we also see an absolute immediate here, which confirms that. LEA is just a regular instruction encodings. For push and pop, we have dedicated functions for that because they're like really straightforward. You don't really need all the aforementioned magic, and there are also not really many things you can relocate here. So we also don't provide any feedback because it's not gonna be really useful. Push and pop, they just differ by the specific constants, so we just instantiate the template here. Also for call and ret, we have special cases, call rel 32 and ret near ret far. For call near absolute, we have regular instruction encodings again. For set, obviously this is not everything. I'm writing a compiler. I've only included those that I actually found a need for. So that's all that I ran into for now. But basically, it's another kind of special instruction. So we'll use the normal instruction encoding class here. It's not instruction encodings because these are always 8-bit. Right? They also haven't ignored mod-rm opcode/reg field, which is interesting. We'll just use 0 as that because we don't like leaving it uninitialized, right? We could leave it uninitialized and whatever, and maybe it will save one CPU cycle. But the C++ standard doesn't really like uninitialized values here, right? And we don't want to mess with the C++ standard. And also, it doesn't really matter. For move 0 extend, this from byte and from word. There's no move 0 extend from D word. It will be kind of pointless if you extend from D word to the Q word. You can just move the register into itself because when you move into a D word register, automatically 0 extends for you. So there's really no point in doing 0 extend from D word. So none of that here. Just the leave instruction. The counterpart to enter that actually gets used. Like nobody uses enter, I've heard, because it's slow. But leave, it's actually usable. Basically, what it does, it pops the stack pointer from the stack frame, right? It restores your RBP register to let you exit the function. This is the test instruction. Because it's also done on the ALU, it's also encapsulated well by our previous helper structs, RMR and RMI versions. This is for the conditional jumps. They all share a similar pattern, so we define a helper type alias here for generic. It's an opcode substitution for 8-bit to base. And for the non-8-bit versions, it's actually interesting. We need to add 10, hexadecimal 10 to be precise, or decimal 16 to the base to get the long versions of the instruction. And we also have a variable width sign immediate for the different rails, like rail A, rail 32. And we have only JZ and JLE here. Again, I haven't found the uses for that, just because I haven't implemented all the comparison operators, okay? And finally, we also have the unconditional jump. And this is by far the most common for just a single displacement. Well, actually, it's an immediate, but really doesn't matter. Like, if you only have an immediate or if you only have a displacement, it's actually the exact same encoding in the binary, so nobody cares. I'll call it a displacement, you can call it an immediate. It's actually an immediate in the code. But basically, we have E9 and EB for the 8 bits, so it's not the same as the previous ALU instructions, like E8, E9, but it's still pretty straightforward. And that actually concludes our journey today in the horrendous yet simultaneously wonderful world of C++ template metaprogramming. Now, this video is intended to be an April Fool's joke. However, all jokes aside, I think that there are genuine benefits to this system compared to other methods like using macros or just typing the overloads out by hand. It provides better compile time diagnostics, provides better type safety, and reduces duplication in both declaration of instructions and the use of the encoding functions themselves. So, whether this video is actually an April Fool's joke is up to you to decide.